at this point, how do we compute transition matrices for diagonalizable matrices, systems or matrices? So A, we know that it's diagonalizable in the sense we know that we can write it as this, okay? How do we compute EAT for this case here? Well, guess what? We are going to start with EDT and then go to EAT where A is diagonalizable, okay? Sorry. We are going this to, we want to solve this question. Is it together? Are we together on what we want to do, people? Perfect. As a starting point, if I've got two diagonal matrices, are we together that the product of two diagonal matrices is still diagonal? Excellent. Perfect. Now, if I take this definition here, and D is diagonal, what is happening? This is diagonal. This is diagonal. This is diagonal. This is diagonal. True? Do you see it? Everything is diagonal. What does it mean? It means that I've got a situation that looks like this one. True? What does it mean? Actually, at this point, everything is going to be 0, and I can take the sum and put the sum together. True? You see it? Immediately. How much are we together, people? 1, 2, 3. And does anybody want to tell me this number here? What is it? This is the Taylor series of what? E lambda 1 t. True? Isn't it the definition? Isn't it the definition of exponential? That means that we have this. That is, in a certain sense, a subset. E diagonal t is kind of putting the E on the diagonal. True? Together? If we are together, let's see this exercise, classical question for the exam. X1, X2, X dot is equal to -2, 0, 0, minus 4x, okay? I start, let me tell you, we start at 5, 3, okay? We start here, and you tell me whether the trajectory will pass through the point 2, 1. Is the question clear? I have this system here, okay? I start from this point, my initial condition x0 is going to be 5, 3. Together? And I've got to verify whether there exists some t such that x of that t is going to be equal to the point 2, 1. Is the question clear? Perfect. I give you a tip on how to do this, and then you do it by yourself, okay? So, essentially, I've got a diagonal system, true? I have a diagonal system. It means that the evolution here is going to be this independent, true? Together? Perfect. So in a certain sense, if I consider x1 dot is equal to minus 2x1, this gives me directly the evolution, true? That is going to be given by this one. And I will have a certain speed in traversing, and I will reach 2 at a certain time, true? And then I have an evolution here. I take the time for which I cross 2, and I try to see if whenever the time that I cross 2 in this direction is the time that I cross 1 in this direction. Do you see it? Go. Computations. Go. Do the formulas. And I come by through. Hmm. Okay, look at me. Where are you, people? Where are you? I am also writing it, but I do not want to disturb. You shouldn't. Whenever I do the computations, am I disturbing you people, or am I making it easier? Would you prefer that I do the computations by myself without showing to you? No. So I do not know if everybody got at this point. I got at this point. I would have gotten at this point. I would have never gotten at this point. I see several I would have never gotten at this point. So, are we together that this one is the trajectory along the x1 axis? Are we together on this, people? Perfect. What does it mean that at a certain, I cross 2? It means that there exists a certain t that I do not know for which x1 of t is equal to 2. Obvious? Obvious. And since this is the general evolution, we need to have this stuff here. True? How are we together, people? 1, 2, 3. Excellent. At this point, I need to find t. Are we together that this one is an operation that you should know how to do? There shouldn't be any doubt. True? Perfect. So at this point, in a certain sense, I found the t. From a graphical perspective, what are we doing? Let's see it from a graphical perspective. We have a trajectory that in time, we start from 5, and we have a certain exponential with a certain decay ratio. True? Together? And this one is going to be my 5e minus 2t. True? Together? And then I'm asking myself, when do I cross 2? True? Together? I need to have 5e minus 2 capital T is equal to 2. Do we see it? Perfect. Now, we were asking ourselves whether for t equals that number, I'm going to have x2 of capital T equals to, what was it, 1. How would you solve it? Go. Is it clear what we are trying to do? Now, yeah, there's a question. So, how many of you see the answer without doing any computation? I see the answer without doing any computation. I do not see, I think I might see if I was given some few minutes without doing any computation, or I do not see it. Look at the situation, people. We have two systems that are independent, true? And then we have something for which this one, this one goes down with a certain time constant. This one goes down with a certain time constant. True? This time constant is double this kind of time constant. It means that the speed, relative speed of this one with respect to this one is double. True? Now I made a mistake. Instead of putting 5, let's put 4. So 4, 2, okay? And then we were having 2, 1. Okay? Now, if this one reaches 2 in a certain t, halves in t, this one, will it half in t or in less than t? Less than t, it's faster. Isn't it faster? Isn't this one faster? Let's do it from a graphical perspective. We have in time initial condition on x1 that is 4, initial condition on x2 that is 2, and then we are doing that this one will decay with a certain way. How is the time constant? How do I compute the time constant? I do like this one. I'm drawing it in a bad way, but you get the point. This is my time constant for x1. It's going to be equal to 1/2. True? Do you see it, people? Are we together up to now? This is 1/2. Okay. If I've got a trajectory here, how do I put the trajectory here? I will go down how fast? My decay ratio is going to be 1/4. True? It's also half. So whenever I do the triangle is going to be like this. It's going to go faster. True? There's some problem in the drawing that I'm doing. Indeed. No, but it has to be 1/4. I'm doing something wrong. Because if I was starting from the same height, sorry. I'm blocking myself, but it depends. It depends on the height. You know that I might have been saying to you something always wrong. That somehow whenever you do the triangle, I was forgetting to tell you that you've got to start from 1. I think I was forgetting to tell you that you've got to start from 1. Anyway, so are we together that this one is double as fast as this one? True? So if we have a certain decay ratio here, the decay ratio here should be double as fast. True? And this means that in a certain sense, this one here, for sure, whenever this one gets to 2, this one will be much below to 2. Do you see it? They're much below to 1. You see, because the relative speed in halving for this subsystem is faster than this subsystem. So, from a graphical perspective, since I was asking, if I start here, do I pass by here? No, it has to do something like this, because this one is faster than this one. Do you get it? Now I will need 5 minutes later on to do something about fixing this time constant thing, so that we do a video on fixing this. But you get the point up to now, people. Are we together? 1, 2, 3.
Sorry.
Question.
To state it like 100% sure, we should see, because I see that one is faster, one is lower, but also the one that is faster has to cover less distance, has to travel less, because it has to travel 1 from 2 to 1.
No, but you've got to think at a halving. Let's do things this way. So, what is the concept of time constant? If I start from x1, 0, after one time constant for subsystem 1, I will be in x1, 0 divided by e. True? And the same here, if I've got x2, 0, after t2, I'm going to be in x2, 0 divided by e. Okay? Are we together? The fact is that this time constant and this time constant is going to be different. This point is here. This point is here. But it's not that I pass through. Okay? Because the time that I pass here, the time that I pass here are two different ones. Are we together? Okay? So, going back to the slides. Whenever I have this object here, I kind of see encoded all the trajectories along the various axes. That means that I know somehow the trajectory of everything. How much are we together, people? 1, 2, 3. Excellent. Questions? Other questions? So let's go to A, not diagonal, but diagonalizable. That means that I've got this system here, and I can write this. Okay? Now, what is happening? Let's rewrite this system so that we write it in the diagonal form. If I have this situation here, let's redo it so that we do all the steps so that you remember. You've got to remember how to rederive those formulas, okay? You've got to arrive at remembering how to rederive. Diagonalizability means that I've got A, V is equal to lambda V, true? I, true? That means if I stack up all the V's, I'm going to have V1, Vn is equal to V1, Vn diagonal. True? Together? So it means that -1. Okay? Perfect. Now, let's write it. At this point, I write x dot is equal to t d t minus 1 x plus bu. True? What is going to be my new variable? My new variable is going to be this one. And how do I modify the other things? I multiply this one times t minus 1, t minus 1, t minus 1. True? At this point, this one is my new variable. This one is my new b. This one goes away, and we have it. Do you see it? Are we together? Are we together on the procedure? Okay? So you start expressing this, and essentially you trace back everything. At this point, for this coordinate system, what are we having? We are having this evolution. So, look out. This evolution here is an evolution along single individual trajectories. So, this is going to be essentially n independent one-dimensional systems. So, this one is diagonal. This is a matrix that will take U and put it somewhere. Let's make an example. Let's make an example so that we see it. Let's pretend that we have at this point these and these that are -2, 0, 0, -4, 1, 2. Okay, B tilde is 1, 2. At this point, what do I have? I have two systems that they are going to look like this one. x1 tilde dot is equal to -2 x1 tilde minus u, no, plus u, sorry, and x tilde 2 dot 2 is equal to -4 x2 tilde plus 2u. Are we together? This one, forced response of this one, convolution. This one, forced response of this one, convolution. This one becomes a vector of essentially convolution. With E. How much are we together, people? 1, 2, 3. Now you should know how to compute the convolutions. You should know how to compute the free evolution and force responses of those single systems. Okay. So you should be able to find, I don't know. Let's pretend that we are working with free evolutions so that we do not have, but we might also do it. We might get x1 tilde t is equal to, I don't know, 3e minus 2t plus e minus 3t, 2t, sorry, convolved with a sine of 10t. True? This might be one. The other one might be x2t minus 4. This one we put 7. Here it's going to be minus 4. And this one is going to be still, maybe it's 3 here. Okay? Because the b tilde is different. At this point, we have the two evolutions. No? We are going to have x1, sorry, t, x1 tilde of t will do something. And x2 tilde of t that is going to do something else. Are we together? This is in time. If I look at it in the phase portrait, I'm going to have something that looks like x1 tilde, x2 tilde, something. That is the first portrait. How much are we together, people? 1, 2, 3. Do you follow me? Are there questions? I saw a few twos, so I'm a bit worried. Are we together that this one is not diagonal? And for now, we do not know how to compute this one. Together? Perfect. Diagonalize, and I arrive at this system here with this diagonal, and this one a different number than before. And this corresponds to a series n single-dimensional systems that are independent. Are we together on this? 1, 2, 3. Now, if I take the first system or the second system, whatever it is, I can compute the forced evolution. True? That means I can compute the trajectory in time. Together? And then I can compute also the other trajectory in time of x1. How much are we together, people? Perfect. Then, if this is my initial condition in the x1 tilde, x2 tilde plane, it means this component, this component. If this is my trajectory of time at t equals to 10 seconds, it has to be this. 20 seconds, it has to be this. Are we together? If we go in n dimensions, I will have n trajectories that are single dimensional. For every t, I will have a 10-dimensional vector. Are you following, people? And then in R10, I will have a point and I will have a phase portrait. If I take the collection of all the t's. Okay? Together? Now, whenever we get this one, did we get the trajectory of this one? No, we need to go back. True? This is something that people very often forget. If I have position velocity and I have a diagonalizable matrix, but it's not diagonal, and then I do the x tilde where I got diagonalizability, and I find the trajectory in those coordinates here are not position velocity. Okay? It's going to be a linear combination of position and velocity. It's not going to be position and velocity. Let's are we together, people? 1, 2, 3. I got a feeling that today is less enthusiasm than yesterday. But you see the workflow. Shall we try to do an example? Is that then you need to find also the eigenvectors and everything is a bit boring and takes some time. Would you like that we go through? Let's make it this way. Per table, you express and write down what is the procedure whenever you start with an A that is diagonalizable but not diagonal. How do you do? How do you find x of t? Force response. Like a total response. Go. Explain to each table and let's see if we are together and then we go together.
Here with this, and then you kind of for the T's. You can do this because you're changing the data space. You're using the eigenvectors as the base.
Shall I go or shall I give some more minutes? 1 more minutes, 2, let's go. How are we, people? One, I go. Sorry, one more minutes. You want more minutes, or two? I go and we continue with notes. Majority of two. So we start with x dot is equal to ax. We express it as t minus 1 x tilde dot is equal to d x tilde. Sorry, what am I writing? Because I write basically this a becomes t d t minus 1. It means that I've got t here dt minus 1 x. This one goes here, becomes this one. This is going to be my x tilde dot. True? This one is going to be my x tilde. The same happens for the u. At this point, what do? I have this object here that gives me the trajectory that is e d t x tilde 0, and this one I need to compute it, okay? And it's the initial condition in the new trajectories, and then I will have to retransform it back. Just a moment, let me rethink it, because if I have t minus 1x is equal to x tilde, it means that x has to be equal to t x tilde. So I multiply times t. I've got to always do it because I tend to mess up very often. And to be honest, finding the formulas, I think it's easier than rememorizing all the cases. Question?
So the overall advantage of like diagonalizing is that we already know the transition matrix because it's just exponentials. That's the advantage, right?
This one is immediate. This one is immediate. There's a catch though. There's a catch. Let's do it this way. This is an important question. I was forgetting to say this. Is t that takes a into the diagonal form unique? No, why?
You can rearrange differently.
Let's make an example. I have a, and I know that a has got lambda 1 is equal to 1 and lambda 2 equal to 2. And then associated to this one, I've got v1. Associated to this one, I've got v2. Anything might be, I don't know, this and this. Now, if I write a v1 v2 is equal to v1 v2 d, this d is going to be 1, 2. Together? But if I write v2 v1 v2 v1, this is going to be this one. True? You see. People, are we together? 1, 2, 3. So there's a problem of ordering. See? Okay. So in a certain sense, we need to define which t, in the sense of which order of the eigenvalues we are going to choose. Shall we do an example? If we do an example with a not by hand, I think that the computations are inside here, so we go through, but we should be together from a conceptual perspective. So the numbers are here. Every step has to be very clear. This one is a spring mass system, and this specific spring mass system has this specific form. Okay? Together? Now what happens? How do we find the eigenvalues? Discuss. How do we find the eigenvalues? Discuss per table. How do we find the eigenvalues? I got it. I would have gotten it. I'm lost. Just for me to see. Perfect. Characteristic polynomial and roots. Do we have diagonalizability? Is this one diagonalizable? Yes, no, I do not know. Discuss. This one, not the system, but matrix of the system matrix. Theta frequencies. Ah, yes. People, what would you say? Very much yes, because this one leads to two eigenvalues that are complex conjugate, plus j or I minus j. True? Together, two different ones, it's diagonalizable. Are the vectors that are going to be diagonalizing the matrix, are they going to be real? No, they will have some imaginary components. Do you see? Perfect. Anyway, how does the phase portrait look like here? X1, X2, position velocity. If I take here, I will do like this. True? Do you see? Are we together with this? Do you remember that EAT is two columns and they go around? How will they go around those two columns? Are they going to do something like this? This is at time 0 and then it expands, and this is at time 0 and then it expands? Or is it going to be at time 0 and then this column goes around and around and around? Do you see that the exponential EAT, if I see the phase portrait that is having some behavior, that behavior is the behavior of the columns of this object here. Are we together? 1, 2, 3. Because those ones, those columns are the trajectories. Because the trajectories x of t is this stuff here. The trajectories are linear combinations of those trajectories. Together, that is the system. This is the system. Question.
But how did you got to the fact that they were going around like in a certain
It's a spring mass system with mass 1, friction 0, and coefficient
no,
1.
No, but from we should check EAT.
Of course. But if I know that my trajectories do like this, I cannot have EAT, or better, let's call it A1 of t, that at A1 of 0 is this one, and A1 of 0.1 is this one, and A1 of 0.2 is this one, and it kind of does something that is an animation that for which it explodes in that way. This one would be a trajectory that in a certain sense has no sense. True? So somehow EAT is a matrix that will have column, 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 column. True? That means vector, 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 and each vector goes around depending on how its components are. What are the modes of the system? Those vectors. Each vector here is a mode of a system. We will see again. Shall we take a pause and then we continue? Perfect. Let's restart at 15.